This conference will now be recorded.
So welcome everyone to another OCP Tap session. This is call number 83. I am joining you today from NIST. It's very nice from our colleagues here in NIST. They gave me a spot to run this call. So today we have a talk by Joran. So Joran is the founder and CEO of TigerBeetle, an open source distributed financial transaction database designed for mission critical safety and performance. So his interests are storage, safety, and speed. Yeah, it fits exactly what our interests are as well. So again, today's talk is about trust and verify, for like detecting clock sync failure in highly available systems. So with no further ado, Joran, the floor is yours.
Oh, thank you, Ahmad. It's such a pleasure to be here with you all, and yeah, to talk about something that I think is applicable, in so many fields and domains. We trust something, and it's also a good idea to verify. And particularly, I thought this is something totally new for me. I normally work in consensus protocols or storage engines, storage, safety, speed. And so I thought this could be a really fun opportunity. We could have an interdisciplinary discussion about clock synchronization protocols. So I'm actually not here to share anything. I'm here to learn, because I think you all know far more about clock synchronization protocols than I do. I've sort of dipped my feet into the papers, so I've read Hagen's, and I love reading about all the peer-to-peer clock sync techniques, and but I've only scratched the surface. So I'm here to learn about clock synchronization protocols, and then also to share some ideas from the other side, consensus protocols. And I think this is really interesting because these are like two different categories. So, clock synchronization, you have physical time, roughly speaking. And then consensus protocols, again, roughly speaking, but you have logical time, you have a total order. So you have physical time and logical time. And I think these categories are very interesting because you can easily go wrong. You can mix them up. You can try and do consensus with physical time instead of logical time, or um, yeah. So what was fascinating to me was to prepare for this. It was a few years ago now that I read Lamport's, clocks paper, logical clocks, time clocks and the ordering of events, I think in a distributed system, and it's such a great paper. And I think I actually read that 20 years ago now. So that was what got me into distributed systems. But what was fascinating when I read that now again was to see how he doesn't only talk about a logical clock in 78, he then starts to talk about physical clocks too, and how you could use logical clocks to think about physical. And I thought, this is very interesting because this is what I want to talk about today: physical time, logical time. And so I'm coming at this from the context of the problem here. I've got, I think, what is an interesting problem, hopefully, to share, or a question to share with us. And the background, for my how I approach these things is seeing that in the OLTP world, the world is actually becoming more transactional than our OLTP software world is. So what I mean by that is you've got all these sectors, or a few sectors, where you're getting 3 order of magnitude increases in scale in like the last 5 years. So it's very rapid, massive orders, and calling for new designs in OLTP databases because the scale is phenomenal. And these are sectors like energy, where because our energy sources are moving to clean energy, we used to think of like, well, we will bill people once a month, for their energy as a utility. But because we're moving to clean energy sources, they don't work like this. So now the way we transact energy must become more flexible, because we must follow the sun for solar prices, so we can arbitrage. So people want to settle energy every 30 minutes now instead of once a month. So it's 1,440x increase in energy transactions. And the existing systems, are struggling to cope with this. And we've seen the same in cloud. We used to buy a server, You buy a few servers and then you would rent them by the month, then you rent them by the hour, by the minute. Now it's serverless per second billing, usage-based pricing. So the volume of transactions across sectors is increasing. That's what we've been learning. And sort of the existing, why TigerBeetle? Why not just use existing OLTP? This is kind of the problem: is you want to do financial transactions, for example, to settle energy, and typically what you see in the existing systems is that there's one real world transaction or financial transaction, and that gets translated into 10 database queries. And in the past, that was okay, but now the scale, the tide is going out, and there are problems. So, one physical transaction, one logical transaction is 10 physical database queries. So we asked the question, what if we turn this around? Before it was one financial transaction is 10 database queries. What if we turn that around? What would it take to do this, so that we can execute 10 financial transactions in one database query? That would be such a nice swing. And then we said, well, let's not stop there. What if we can do 10,000 financial transactions in just one network round trip, just one database query? Just like that, you flick them across and you've done 10,000, because that's kind of what you need to do actually to cope with these volumes. So you've got 3 orders in the K. Now you're just keeping up, and then you've got an extra 10 margin of safety, and you always design for the next order of magnitude. So 10K financial transactions, one database query. And this is really like the key innovation in TigerBeetle, is to say, the language, how we talk to the database. If we can change this, we can invert the scale equation and do some interesting things. So that idea, that what I've showed you, it's the real heart of TigerBeetle, and that's what started it as an open source project, and now as a company as well, around Apache 2 open source. So this is the whole mission: track financial transactions at scale. And by scale, we mean 3 orders of magnitude. And by financial transactions, we really just mean OLTP, so business transactions. OLTP, tracking business events, not necessarily in fintech. It could be in energy sector again, or gaming, or cloud, where you're doing usage-based billing, anywhere where you're trying to track business. So this is the language of business, business transactions. There's counterparties, there's the what, the when, the where, the why, the how much. And if this was something very surprising to me, but this is kind of what you really need. This is the essential schema for tracking these transactions. And this is actually double entry accounting, which is the centuries old schema that has always been used. What is the best schema to model business events? Well, in the real world, on paper, this is how it's done. And this, again, this lets you track the who, what, when, where, why, how much. Plus, it gives you financial consistency, not only raw row level consistency. So it's far more suited to maybe where OLTP is going. And using these primitives, this is what we've done in TigerBeetle, because these double entry primitives are so simple. The schema is so simple, but also elegant to capture everything. To model a business, it's the essence. You can pack 10,000 of these in a 1 meg request and send it through. 1 meg is great for sequential writes to disk, great for network, great for amortizing your consensus control plane. So again, this is the idea. Let's fix the impedance mismatch. Instead of 10 physical SQL queries to do, one double entry, it's essentially double entries is what these places that we were looking at, that's what a payment switch we were consulting on, that's what they needed. Let's just give them these double entry primitives. And obviously, as you know, like time, especially in the financial world, but in the business world, financial transactions are mission critical. And I'm kind of getting to the problem, through the lens of consensus. How do we have an interdisciplinary discussion around clock sync and consensus? This is our lens. So TigerBeetle, mission critical. We can't have a single node database anymore. We can't have manual failover. What you really need is replication for durability. Like you can't have something only on one data center. You need it across data centers. And so when transactions come in, like a megabyte of these, a query comes in, We write it to the primaries disk plus a backup, and that's synchronous. And then we commit and we act to the application. And obviously, this is view stamped replication. It's this was actually 88, so 10 years after the Lamport paper. Brian Oakey, his PhD thesis, he figured it out. The first one to figure out consensus in the face of network partitions. And network partitions are going to be the theme for today for this talk. I will get there. That's a bit of a clue. But so he did this with Turing Award winner Barbara Liskov, and then years later, 2012, Barbara Liskov revised. They sort of just represented view stamped replication, and she did that with James Cowling. He's now he was at Dropbox, now CTO of Convex. And the interesting thing, if we look at this in terms of time, we always think of Paxos, but actually view stamped replication was a year before. And Paxos even would only get published in 1999, I think. So another 10 years later, because VSR was really first. And then again, the revision of VSR was 2012. And if not many people have read this paper, Raft is famous, but if you've read View Stamped Replication Revisited 2012 and you compare it with the Raft paper, it's so close. You almost get the feeling that Raft was written first, then view stamped replication. They're so similar, and yet it's the other way around, so Raft mentions view stamped replication, but yeah, this is I love it. Both times it was a year earlier and then 2 years earlier, and yet not many people are familiar with it. But this is what we use in TigerBeetle, and let me just go on now. So this is what makes TigerBeetle a cluster. This is how we get multi-AZ availability. And obviously, the architecture then is, you might not know this, you might know this, but this is just the term if you want to go and look it up. It's the classic way. If you want a database cluster, this is your architecture for the database. It's called a replicated state machine. State machine is just a pure function. Given the same inputs, execute them in the same way always, and you get the new state, the new output. And you run this function on all the machines. You give all the functions a totally ordered log, and they will all reach the same state. So this is the architecture. The primary will append to the log. It'll wait until it gets a replication quorum, 2 of 3 or 3 of 5. And once it's got that, it commits and it executes the business logic. And because you've got a quorum, if you elect a new primary later, the totally ordered log is guaranteed to survive, and you won't lose what is committed. But this is the basic architecture. So it's not so important, but I just wanted to give you the background. What is important is the actual business logic. So if we forget the consensus for a minute, what is the actual business logic that this state machine executes? If we look at the function, what's the code? And again, it's business transactions, financial transactions, double entry accounting primitives. And it's double entry within systems to track money movements or movements of value. So you don't have to only use TigerBeetle for money. You could use it for rate limiting, for quantities, anything like that, for inventory counts. So it's to track this within a system, a whole system that the operator controls. But what we noticed is that, for example, a payment switch also needs to track money movements between systems. So this is where you are one legal entity and you have your infrastructure that you control, your databases, your tech stack, and you need to move quantities to other systems that don't have the same tech stack. How do you do that? And this is a sort of two-phase commit protocol at the application level, at the business logic layer. So not consensus. We're just talking, how do you move money, like real money, between payment systems? And it's like a two-phase double entry. So it's like a two-phase financial transaction. And you sort of see this in the real world, a credit card transaction. There's 2 steps. You authorize, and then a few seconds later, it gets captured. So the authorize is going to make sure that the funds are there. And then once they're there, yes, they're there. And then it gets captured. And if the person who is trying to obtain the funds, the person who's being paid, if they don't capture, there's a timeout, and the coordinator will then roll those funds back. So you authorize, you reserve the funds subject to a timeout, so that if the payee doesn't come back to claim what is authorized, the funds will roll back to the payer. So I'll say that again. So this is a financial transaction. You're moving money from the payer to the payee. They run different tech stacks. What you do is you reserve the funds on the payer's tech stack so that it can't be double spent for another transaction. And then the payee comes back and says, yes, okay, I'm also prepared. And now let's do this. Let's capture. And if they don't, if the network fails or whatever, there's a timeout and it rolls back. And I think now we're getting into physical time. So far we've been in the land of logical time. Now we're coming into the land of physical time, because these real world transactions, they depend on physical time because the funds must be reversed. If something goes wrong, after 24 hours or after 30 minutes or n seconds, the funds must roll back. Otherwise they get tied up. And here is where timestamps, physical timestamps, become important. And again, not consensus. It's important because if the time is wrong, if you authorize the transaction with a certain timestamp and it times out relative to that in seconds, and then later the clock jumps around into the future, into the past, it could be that now you wait a year and someone's money is locked up. And this happens, and then you need manual intervention, to come and release liquidity. So the other challenge here is, I've described the replicated state machine architecture for you. And again, it's pure functions on machines. They have deterministic business logic, and they process the same log and they get to the same result. And again, now you must be wondering, but, how do you deal with physical time? Because within the state machine, within the business logic, how do you deal with physical time? Because these machines have different clocks, and the business logic across them must be deterministic. Otherwise, some machines in the cluster will expire, some won't, and you're going to have split brain. So how do you deal with time in a replicated state machine environment? And the answer is, this is just backdrop again, context. The answer is that the primary, as the request comes in to process a transaction, to replicate it, before it's replicated, the primary timestamps it with physical time. And again, we've got two concepts here, two categories. We're not mixing them. So we're not trying to use physical time for consensus. What we're doing rather is, before we replicate, we add the primary's timestamp to the data that is replicated. So then all the machines in the cluster, the business logic, will see time in the same way. So you're pulsing physical time through if your business logic uses physical time. And there are state machines, obviously, where physical time is also important to the business logic. So if you want to learn more about this, there's a great talk, Martin Thompson of Almax Eran, and it's called The Evolution of Financial Exchange Architectures, and he gave it at QCon in 2020, just as we were designing TigerBeetle. And this is sort of the way that you do it. If you need time, and again, consensus is a lower layer. Consensus is already giving you total order. You're not using physical time for total order, but you still need physical time for your real world business logic. Money must be expired after n seconds. And this is how you do it. The primary will timestamp the financial transaction, and then the cluster can expire that deterministically. And like, Uncle Ben said, time is money. So if the primary's clock is wrong, people's money, is going to be locked up. And here we are. So clock synchronization is important. These are two separate categories. We're not making the mistake. You do get this. So some consensus protocols try to cut corners on strict serializability. They say, well, we're going to sync our clocks, and then that's going to give us faster consensus. But this is not what I'm talking about, just to be clear. This is about clock synchronization in the state machine business logic, and the consensus total order is at another layer. So this is physical time, and it's important for liquidity. This is the example I've given you, where people's liquidity is held up if we get this wrong. And it's even just important, it's regulated, compliance, auditing. Roughly, you want more systems in the real world to have similar timestamps, then auditors can print it out on paper and double check things. A logical clock can't be used for that across systems because it doesn't have meaning across systems. So that's why it's important. And then again, the layer below, consensus is important. This is how we get total order, strict serializability, high availability. So we've got physical time, we've got logical time. We're not making the mistake of mixing them, but both are important and they're actually all part of the discussion. And again, a clock sync protocol does not a consensus protocol make. So, if we have a perfect clock sync, that we shouldn't use that as a consensus protocol because clocks can fail and then strict serializability is violated. So that's why we don't mix physical time, logical time. But there is a common denominator. And I think, we've hinted at this. Both protocols are impacted by network partitions. So consensus is designed to be highly available. This is something that people have lost, and it's been muddied by the CAP theorem, which I'm not a fan of. And CAP theorem is something very specific. It's got very specific definitions. But actually, if you read Brian Oakey's PhD thesis, 88 view-stamp replication, the title always surprises me. It's view-stamp replication for highly available distributed systems. And actually, in those days, when people were really wise about distributed systems, like 78, Lamport logical clocks, 88, Brian Oakey, it was just table stakes that you're going to have consistency. There was no concept that you're going to try and violate it for scale. It was just, it's assumed. And so the problem was, well, how do you have strict serializability in the presence of network partitions? So we want consistency, we want high availability, and we want to be partition tolerant. And now it seems like I'm violating CAP. But actually, the key is that these things are a spectrum. So consensus protocols can tolerate partitions up to F failures, up to F machine or link failures. So you can have strict serializability, you can have high availability up to F. And CAP, has a totally different view and different definitions, and so we all talk past each other. There's like the consensus world, and then then there's CAP, and often CAP leads you down a different path, which is not consensus. But anyway, that's a little bit of a side note. So consensus is really designed to give you consistency to be highly available in the face of network partitions. And this is now where we're getting, to the problem. I don't know if you can spot it. So clock sync is important, consensus is important, consensus is highly available in the face of network partitions. Clock sync is also vulnerable to network partitions. I'm just treating clock sync here as a black box. We're not making any assumptions as to how this database is operated. Maybe it's running on Raspberry Pis, maybe it's running on cloud hardware on-prem. We don't know if the operator is using Crony, NTP, PTP. We don't know what they're using. Atomic clocks, we make no assumptions. We assume they are running some kind of clock sync, but otherwise clock sync is a black box. But like any software, it's vulnerable to network partitions. So what is the problem? So clock sync solves for clock faults. That's the goal. Consensus, and this surprises people, but consensus solves for network faults. TCP actually doesn't give you consensus. If it did, we wouldn't need consensus, but TCP doesn't really give you total order across connections. So consensus solves for network faults. Clock sync solves for clock faults. And here's the problem. Obviously, clock sync, you get amazing protocols that are designed to be robust and fault tolerant. And so is consensus. But the fault tolerance of these protocols is not aligned exactly. It's not exactly the same. They handle network partitions slightly differently. So you get different availability guarantees for clock sync and consensus. And that's fine if your consensus goes down, because if your consensus goes down, your business logic is not processing. And the reason that you needed clock sync in the first place is moot. So you have clock sync, fine, clocks are synced, fine. consensus is unavailable, okay. And the problem is the other way. Consensus, you get some kind of partial network fault. Your consensus is so trying to be highly available that your consensus is running across two other AZs. One AZ is down, another link in the other AZ is down, but flexible quorums are being used, so you can tolerate even 3 out of 6 failures. So consensus is still running, but whatever is causing those network faults is also interfering maybe with the clock sync hierarchy. So clock sync is broken, or clock sync is just broken for one machine. It's not being synced. And now you've got a problem. This can be dangerous because you're processing transactions that maybe, are required for compliance to be within a certain, clock accuracy. And we're trusting the clock sync, but we don't know. The consensus is not verifying. The business logic above the consensus is depending on clock sync, and consensus is providing physical time because the state machine needs it, and it's trusting clock sync to do it as it should. Like, I'm not proposing that consensus should replace clock sync. They're too, there's too much. It's both fields are, massive fields. But the problem is consensus is trusting but not verifying. And so consensus is only thinking about network faults but not about clock faults. And yet the business logic on top of the consensus is depending, on these things. So this is the problem. What if the clock sync fails, even just to sync the primary, just one machine? You only need one clock fault to ruin everything, because many of these consensus systems, they have one machine as the primary, 1 of 6, 1 of 3, 1 of 4. Again, flexible quorums. So just one clock sync, you just need the primary's clock to stop being synced and just to have a fault, and it jumps a year ahead and liquidity is locked up. So the solution is trust, let the clock sync do its job. The operator is going to deploy state of the art, but we need to align the consensus availability with the clock sync availability. So if clock sync goes down, consensus must remain unavailable until they come up. This is the idea that we sort of experimented with in TigerBeetle. This was 2 years ago that we started with this, and this is the idea. So you have these consensus protocol messages already, and let's piggyback on them. These are very small messages. They're not subject to head of line blocking. And actually the consensus, there's many things in the consensus world that get a lot better if you know something about the network topology dynamically, because network topology changes. So your round trip times change. You want to actually know your round trip times between nodes, because that helps you adjust your consensus timeouts. Otherwise, your network can become very slow and you're going to start view changing and deadlock. So it's very important in consensus. So much you can unlock, the more you can become. You don't have to be perfectly aware of network topology, but the more you know of the network topology dynamically, the more you know your round trip times, it helps the consensus. But that can also help you to verify clock sync. And you don't need to be precise. Clock sync can be orders of magnitude more accurate. It can be nanosecond precision, microsecond precision. The big idea here is, like with 10-second precision, after 10 seconds, let's detect that the clocks are all bad across the cluster. We've had 3 out of 6 clock faults or something. And you can do that obviously with Marzullo's algorithm. So this is the idea. We're not trying to clock sync. We're just trying to know after 10 seconds that things are so bad, the cluster should shut down. It's a verification mechanism, just a defense mechanism. That's it. And this is how we do it. This is probably something you've all seen. This is server 1, server 2. And you've got round trips between them. These are just consensus messages. You stamp the consensus message in software. Again, we're not making any assumptions as to hardware or software clock sync. Obviously, hardware, there's more you can do. This is just poor man's verification. So stamp it with a monotonic timestamp, stopwatch start, stopwatch end. Now you've got the one-way delay if you divide in half. And then obviously there's things you can do. You can reject bad samples, choose the smaller, with exponentially weighted moving average. You can, choose the more recent round trip times, sliding window. And then you've got T1 and T2, which is wall clock time on both machines. And you can start to figure out your clock skew and then use that with Marzulo to get a picture of how many clocks in the cluster are in agreement. Or if you start seeing things that clocks are all over the show, well, you can start to notify the operator. And then at some point, you can start to actually shut down automatically because you don't want to be moving with high velocity if your clocks are, years out. That you don't want your primary timestamping then, because the timestamps are not worth it. So fail fast is really important, especially the night capital incident. So here is an example. So this is a client request coming into the cluster. It's about to be replicated. And before it's replicated, the primary checks is real-time synchronized, by which we mean, is it like within even 10 seconds across the cluster? Do we have a rough idea? Or are things so bad that we should just wait and remain unavailable? Let's align ourselves. It looks like clock sync has definitely failed. Or you can riff on this and change it and say, well, clock sync looks really bad from my perspective as the primary. Perhaps I should abdicate and do a view change to another. And those heuristics are, that's a whole another piece of work, figuring out when is the right time to do that. You've got to be careful and balance that. But you can, this is sort of the rough idea. Let's verify. And if you know that the primary's clock is so bad, perhaps you do want to actually move to hardware that's not faulty. And so again, just to be clear, the goal is not to re-implement clock sync, just to verify that it's available and it's within error bounds, where these error bounds are orders of magnitude less precise. And this is just the phrase, 3 clocks are better than 1. You use this in consensus, and now you're trying to, within the consensus protocol, be aware of clock faults. So if you want to read more like the actual way we do this in TigerBeetle, it's part of VSR in our implementation, and it's clock. And the nice thing is it's written in Zig, so it's not long until the weekend. If you would like to go and have fun reading this new language called Zig, then this is all in Zig, which is very nice to read. And we've written a blog post about it as well, which is how Amat got in touch. 3 clocks are better than 1. And I want to just end off now as we finish. Here's a question. This is like a trivia quiz, so which I always love these kinds of questions. I hope you do. So the challenge here is, okay, given T1 and T2, we know, sure, clocks are going to be skewed. They're going to be drifting. So we can expect these to give us, wildly different results. M1 and M2, this is where we need like a stopwatch, a monotonic clock. And here's the quiz, right? So what is the monotonic clock on Linux? How do you get like a stopwatch clock on Linux? What's the way to do it? So we actually asked people, this was 2021. We said, what's the monotonic clock on Linux for a distributed database to measure elapsed time? You just want a stopwatch. That's all. So obviously, is it clock monotonic raw, clock boot time, none of the above? I think none of the above. People were just clicking. They wanted to see the answer. So we'll discard that. About 50%, said clock monotonic is obviously the clock monotonic on Linux. And Jepsen is famous for breaking distributed databases. And you get this idea from Jepsen too. Here's the Jepsen report for Yugabyte. Using clock monotonic for leases insulates Yugabyte from classes of clock error. So, this is what you want, according to Jepsen, use clock monotonic. Another Jepsen report for error spike. So the latter is useful for triggering timeouts. And these are some of the strobe, where Jepsen is used to test databases. It messes with things, messes with time, strobes the time. And doing that is useful to try and confuse short-term latency measurements in code, round-trip measurements in consensus. In code that doesn't use clock monotonic. So implied clock monotonic is what you should use. And then this is a classic, distributed systems book, Martin Kleppmann. He's written a lot about time, some fantastic blog posts. Also, just how badly things can go wrong with time because of GC pauses. So in this book, Designing Data-Intensive Applications, Chapter 8, a monotonic clock is suitable for measuring a duration, stopwatch, such as a timeout or a service's response time, clock get time. Clock monotonic on Linux are monotonic clocks. So this is sort of what we learned, and this is what I expected too. What would you say? What's the answer here?
I will
This is an
say
ask.
clock monotone and raw.
Okay. Clock monotonic and raw. Anyone else? Everyone agree, and who doesn't agree? So I would have said the same. And I love this quote by Mark Twain. This is the opposite of consensus. So whenever you find yourself on the side of the majority, it is time to pause and reflect. So
Amen.
I love that. Yeah. Whenever you find yourself on the side of the majority, it's time to pause and reflect. Mark Twain. And the Linux manual is not on the side of the majority. So you start off, you read top down, you read clock monotonic, great, I've got my my monotonic clock. You carry on reading the man page, clock boot time. It's identical to clock monotonic, except it also includes time that the system is suspended. So actually, this is a better monotonic clock. This is really what you want. Clock boot time is suspend aware. So why
But
isn't
do
it
you
like
want
this
to
in
have the
Linux?
suspend aware? Do you want to have the suspend aware? Like, I think you don't want to have the suspend aware because let's say as you're suspended, the travel happens, right?
You're quite right. So there are contexts where you don't want it. Like if you're using a timeout within a single machine, a single process, you don't want to be suspended and suddenly you've got a million timeouts that fire in your JavaScript code. There you want clock monotonic. But in distributed systems, when you're trying to measure time across machines, you actually do want to be suspend aware because you might have used it for a lease. And now you don't know that actually, you took a lease out for 24 hours, but you don't know you were being migrated on a shipping container to Antarctica for like 2 weeks. And then you come back up and you think the lease is still held. Obviously, like Kleppmann has written about using fences. That would be the better way to solve this for this reason. But this is where you do want clock boot time. And actually, there was a patch, Thomas Gleichner 2018. Let's make the monotonic clock behave like boot time. And it was really historical, that clock monotonic didn't do this. And boot time is really what it should be. So obviously the kernel was patched, and then Linus reverted that, which is why it isn't patched today. So clock monotonic is not clock boot time, and it's exactly what what you were saying. Revert it because user space was relying in some cases on, you didn't want a million timeouts firing if the timeouts were local to the machine. So there's like this conflation of local events and global events. So despite our hope that it won't, but it broke user space. So anyway, so both are valid. Clock monotonic is valid if you're not a distributed system, perhaps. If you are, then chances are, and you're trying to measure round trip times or things like that, clock boot time is more accurate. So just a little bit of fun trivia,
So
something we learned.
Clock underline boot time is more like clock underline uptime then.
Excuse me, Amat?
Is that right?
I didn't catch the
It's more
last.
like clock underline uptime. It's more
That's
like
it.
the boot time here, like because it's aware. Yeah.
It isn't uptime.
Right.
It is a monotonic clock. So you use it as a stopwatch. So you don't think
Yes.
of it as, seconds since boot, but it's using that to give you a better stopwatch.
Yes.
Because
Yes.
clock monotonic as a stopwatch is going to freeze even though time is elapsing. In the real world, time is
Yes.
elapsing, but clock monotonic isn't going to measure that. Clock boot time
Yes.
will, because
Yes.
it's linked to uptime. So you've got it. Uh, so yeah, for distributed systems, probably, and the kernel did try to fix this for everybody, but just historical reasons, user space reasons, one needs to know. So actually, for Yugabyte, for the Kleppmann book for Aerospike, they shouldn't be using clock monotonic because they've got gaps in their timing because they're using it in the distributed sense. There, they really do need to be using clock boot time. So I wrote to Carl Kingsbury in 2021, to just to let him know about these reports. Yeah. And again, just to clarify,
Very
because
interesting.
people easily get this confused, we're not talking clock sync to try and cut corners in consensus. The two are different categories: physical time, logical time, different layers, different categories. But yet we can have an interdisciplinary Q&A. So yeah, any more questions? Happy to. Now here's where I want to learn from you. Should we be using PTP? I think the answer is of course. Yeah.
Yeah. So it's also let's see any floor like questions from the floor. Hearing none, I think everyone is a little bit shy. Let's do some icebreaker. Yeah, I'll start with a question. So um, let's say you have the need for precision in your system, and then you're providing the precision with the hardware timestamping. Do you believe, like, let's say if you don't have hardware timestamping, you still can get away with it by increasing, I don't know, whatever methods and so on? Like,
I think you all know better than me, so I wouldn't prescribe. I would say if you can do hardware timestamping, you probably want it. And I think you shouldn't use software. If you require hardware timestamping precision, you shouldn't use software. Maybe I can be corrected because I know there's some exciting stuff like Crony is getting accurate, and Higgins also was pretty interesting, I think. But yeah, so you want to definitely trust the hardware timestamping, and then you want to verify it at a far coarser precision,
yeah.
uh, on the order of tens of seconds. But it's more that after 10 seconds we see that the clocks are so bad, and obviously we've taken into account head of line blocking and network congestion. We've got good round trip estimates.
Mhm.
And it's more like, can we verify and then alert the operator, just to have some mechanism that we're not running blind. Like how do we verify? Yeah.
Yeah.
And I think what you can do this on the clock sync side as well,
Mhm.
where you could verify from the clock sync that you are able to sync the primaries machine, and probably
Mhm.
both sides can be verifying more. Defense
Mhm.
in depth.
Mhm. So also another thing, like you brought up like the cap theory. There's also this cal theory that tells you basically the the clock skewness, as long as it's better than latency, you're done. Basically, you don't need more. Like, let's say for distributed systems. What do you think of that?
If you is that, if I understand correctly, so you're trying to get your clock sync precision down to be the same magnitude as round trip latency?
Yeah, like let's say you have a network, and then you have uh, I mean different latencies, but then the shortest you have between two nodes, let's say on a connected on the same like let's say rack, just a round trip, I mean round detour, basically you go to the tour and come back, and you have, let's say, I don't know, 5 microsecond, and let's say with the consideration of Nyquist, let's say you get a clock skewness of 2 microsecond, and now anything better than improving basically like your clock skewness from that point, do you think would it have any value, or just from your vision on this?
Yes. Yeah. So if you try to do clock sync using the network, but the network resolution is coarser than your clock sync.
Uh, no, the coarseness that comes from the timestamps. Like let's say you have hardware timestamp, and that's
Okay.
basically what I like about hardware timestamps, because like I believe, I mean, it's not like I believe it, it is like from,
Yes.
it's how it's
Yes.
driven.
Yeah. Good.
Like the
Good reasons. Yeah.
the variance you get from latency will affect the performance you have in your clock skewness, the variance.
Absolutely.
So now
Yeah.
if you don't have a like a hardware mechanism to timestamp at ends, you're not going to have a required precision to calculate RTT. And if you don't,
Yes.
then no algorithm in the world can improve your precision, because that's against information theory. Like basically
Yes.
information doesn't exist. So you're creating artifacts. So artifacts are not representing the information. So I mean,
Yes.
this simply from measurement theory, that no matter what algorithm you come up with, when you do measurement, the precision is not going to increase. You can always decrease actually the precision. Like processing always
Exactly.
destroys information, doesn't create information. And
Exactly. Yes.
I mean, and I'm always interested to hear like there are, let's say, things that might, be, and there's not exception. There's no exception in science. It's just like another combination that might create, I don't know, something. I don't know about those, and I'm always curious to hear about those. But so far, again, let's say you don't have that info. But then now going back to the clock skewness, right? So if you are better than the latency that's between the machines, well, great. Now you have a good way to provide linearizability. But now going further, do you see applications where they might take advantage of a better clock, let's say an order of magnitude better than the lowest latency?
Uh,
And this is latency,
I'm,
not
I'm,
very.
yeah, yeah, I'm sure there will be. So, for example, like, some, especially in like fintech, you can, you're required that you need a certain precision, and
Yeah.
that's not something that maybe you want to lean on software timestamping for, because of all the factors that you've raised. So again, you want to trust the hardware timestamps, um, but is it enough that a human must manually verify that how do we check that the clock sync is working in the face of network partitions? So we've got accurate timestamps, but maybe we don't even have a network. So there is, how are we syncing time to this fleet of machines? What if there's one machine and something is going wrong, because things always go wrong, and that one machine happens to be the primary of a highly available cluster, and the cluster is just going to keep running? What is the mechanism that we have to verify? So we trust the hardware timestamps, we trust the best clock sync available, and I think people are always going to want it just to get better and more accurate, more precise. So we're not trying to re-implement that in software, but rather with orders of magnitude less precision to verify. So it is possible in software to get certain levels of clock sync precision. So we even thinking worse than NTP. Let's be 10 orders of magnitude worse, and that's still like, I don't know, is it seconds? And then let's say, okay, well, our maximum tolerance for clock faults is 10 seconds now. So things would have to be so bad, but then your verifier will pick it up. Like the whole factory is on fire at that point, but at least you catch it within 10 seconds. But otherwise, maybe you're waiting 45 minutes for human intervention, manual intervention, because the markets have said to you, no, there's something wrong. You've tied up liquidity for 45 minutes because one machine had a clock fault. It jumped a year into the future, and the consensus never picked it up. There was no verification. So for sure, like you say, we want to trust. Don't try to second guess it in software if you've got hardware mechanisms, but we still need a verification layer. And can we do that in hardware too? That would be interesting. Can the clock sync crash the primary machine just at the hardware level? Let's crash that machine if clock sync isn't working, because at least that way, other consensus protocols that don't have these defenses, they will be okay. But at present, they will just run, and the state machines that use physical time. So it's a tricky. It's very like a. I'm always wary when we speak about it, because on the consensus side, people will say, "Oh, you're doing clock sync to shortcut strict serializability," and on the clock sync side, it's like, well, we've got more accurate synchronization mechanisms, but this is just defense in depth. Like, again, the clocks are they're so far out that we should be able to detect it. Yeah.
Wonderful. Any question from the audience? Go ahead, Mark. You cannot hear you, Mark, I think.
Is it better now? Okay, perfect. So thanks for the talk. And I was wondering, why did you choose Marzullo's algorithm? Because I would be very interested in the fault model, in the analysis of Marzullo's algorithm, if you also consider faulty and faulty processes in the network, and especially Byzantine fault tolerance properties of the entire synchronization.
Yes. Thanks, Mark. Yeah. So Marzullo is also a sign, that this is verification. We're not attempting clock sync, because there's better algorithms, and we just wanted something simple at the 10-second granularity. So, you can. I mean, it actually works pretty well at the second granularity too. But Marzullo was just something simple, like not. We applied some techniques in how we measure the samples to throw away some ideas from peer-to-peer clock sync, because the spirit of TigerBeetle is to be able to run on any kind of hardware, very small hardware. So it's fast but small, and it uses commodity hardware, so we don't make assumptions. But we try to so kind of like from the papers on peer-to-peer and Internet of Things, how they do very simple clock sync, but it's actually quite effective. I'm always interested, how can we obviously hardware is so advanced, software is always lagging, but how can we just do better with software to make the best of commodity? So Marzullo was something very simple, and then we've augmented it with one or two tricks on how to correct those noisy samples. But we can do better. So I would love any suggestions for us, where, and also if it's all open source, clock.zig, so TigerBeetle repo source VSR clock.zig, and we'd love like collaboration, like if anyone wants to come help us hack on this and we can run experiments. We've actually also built a deterministic simulator, so we can simulate a whole TigerBeetle cluster in a deterministic simulator like Foundation DB did, and we can actually inject all kinds of simulated virtual network latencies, and we can measure the clock sync accuracy. So we wrote a packet simulator to run this in and check that it works. But we've only scratched the surface. This is like our experimental idea. We're just trying to answer this question: how can we verify? So we'd love, like, if you want to come and join us in the repo, please do, and we can take it to the next level. We're probably going to have some measurement bugs, and we'll find that. So I would really love to get everyone involved.
Yeah, thanks a lot. Yeah, I'll definitely take a look at this because we are also working on fault tolerance clock synchronization in networks, and uh, incidentally, just last week we also started a project to do a deterministic simulation of clock synchronization, and so it will be very interesting to have a look at your approach. So thanks a lot for the hint.
Oh, that's fantastic. Yeah,
Yeah, no, it's perfect
is
timing.
it? Yeah, that's great
Yeah,
because it's
yeah,
so nice. We've used deterministic simulation for testing.
yeah.
We do fault injection of storage faults, network faults, but it's so nice to use it for performance testing because now you get a predictable, noiseless measure. Your testing environment is pristine. You can
Okay,
simulate
yeah.
everything, and it's we again just scratching the surface. So we'd love to compare notes. Yeah.
Oh, that would be great. Yeah, thanks a lot.
Wonderful. Any more questions? So another question, like for me, Joran, what do you suggest? Let's say when you have all these nodes maintaining their time, like let's say a validation, I mean, just like abstract. Let's say I want to have a validation of the nodes on their clock, and this is not necessarily for clocks that they drift due to errors or something. This is more like if you have bad players and they're trying to have
Yes.
their clock, like how do you want to go
Yeah.
about that? And also, like this is a challenge that I'm facing. When you have everything open source, you're more vulnerable actually to that. How can you still maintain, reliability against bad players while you are also an open source?
Yes. That's a great question. Yeah, I realize I didn't fully answer, Mark, your question on Byzantine fault tolerance. So, and that's kind of your question. I might like just
Yes.
helping me out. So thanks. So I think like answering it in LIFO order. I think hackers are smart. Even if stuff is a black box, they've got great imagination. They will know what's behind the non-open source. They're great at that. So hopefully, at least open source, we can get OCP taps help, and
Yes.
fix these things. But I think, yeah. So just to be clear, TigerBeetle is not Byzantine fault tolerant because um, we could go into that. There are BFT versions of use-stamp replication. In fact, Barbara Liskov pioneered that also with Miguel Castro. Practical Byzantine fault tolerance. It's actually view-stamp replication made Byzantine fault tolerant. So again, like 3 times they were just there. But yeah, so TigerBeetle is non-Byzantine fault tolerant because that's a lot of these systems are like that. Perhaps in future we could make it, we could just increase the redundancy. And the other angle is that we do have a concept in TigerBeetle of what we call near Byzantine fault tolerance with respect to the disk. So most databases don't have a storage fault model. If they just assume they use checksums to handle to provide crash consistency through power loss, they don't really use checksums like ZFS used checksums. ZFS did this properly, but most databases are not ZFS. They can't handle what ZFS handles. But TigerBeetle, we've been inspired obviously by ZFS. So we do have a storage fault model. We can handle corruption, 8% corruption. Sectors get written over other sectors. We're fine. We can handle that and we test that. But so that's where we're kind of like practically near Byzantine fault tolerance. But if someone wants to so TigerBeetle is running in a trusted environment, and it's not Internet of Things. It's 5 machines. It's the core ledger, core banking, that kind of system. So it's trusted environment. We do a lot of hash chaining. If the code, if there's some reason that, the code, obviously ECC memory, but if things still go wrong, we've got 3,000 assertions. So while and this is where we get the idea of clock verification, is that every function that runs is checking all the other functions. We assert the inputs, the outputs, interim states, 3,000 assertions, between 2 and 6 on average per critical section of code. So we follow the NASA Power of 10 rules, safety critical code. And also, just to add, what I didn't mention is we do static memory allocation. So we don't do dynamic allocation after initialization. So there's no, the latencies are very hard in TigerBeetle, which helps. We don't use a GC language. So yeah, thanks. Great question.
All right, we're on top of the hour. Any more question? Hearing none. Joran, thank you very much again for this amazing, informative presentation, and we'll have the recording, and hopefully you send me the slides all available on the wiki.
Will do. Thanks so much for having me. Great to meet you all.
Great stuff. Thank you.
Thank you.
Thank you.
Bye-bye. Bye, everyone.
Thanks.
Thanks.